Section 3.4 is about linear programming. Linear programming is when we have multiple functions that are graphed and we have to find the maximum and the minimum values of a region. Over here you see a triangle that's created from the intersection of three functions. A couple definitions we want to talk about. The constraints are the boundary lines that are the outside of the region. So the blue lines here are my graphs of my constraints. The feasible region is the orange part here. It's the shape that's created when you graph the lines. The vertices are the points of where the lines intersect, and they're the important points because the maximum and the minimum values of the function always occur at the vertices. This function that you see here is called a bounded function because the shape is a polygon. There are no open gaps that go on forever, but there is such a thing as an unbounded region, and we'll see an example of that in a little bit. Now this example has a lot of stuff going on, so we'll try to attack it piece by piece. First we want to graph the following systems. X is greater than 1 means we want to graph the line x equals 1, which will be a solid line here at x equals 1. And the region we want to graph, since x is greater than 1, if I put a 0 in, 0 is not greater than 1, so 0, 0 is on the bad side. So I'm going to shade this to the right. Now the reason I'm not doing any shading is because I'm going to wait until I've graphed everything. So there's x equals 1. That's my first boundary line. My second one is y equals 0. That's this horizontal line. I can't use 0, 0 to try that one, so I'll try 1, 1. No, I'll try, well, actually, I'll try 2, 1. So if I plug 2 in for x and a 1 in for y, it works. So that means I'm going to shade above this line. So far I'm to the right of the x equals 1 and I'm above the y equals 0. Last one is this one. I'm going to make a boundary. 2x plus y equals 6. Subtract 2x. So y equals negative 2x plus 6. That means I'm going to start up here at 6. That's my y-intercept. And then do a rise of negative 2 to the right 1. Negative 2 to the right 1, negative 2 to the right 1. That's going to be a solid line, so I'm going to graph that. I'll just sketch it here. And then you can see if I plug in 0, 0, 0 plus 0 is 0, and that's less than 6. So 0, 0 is on the good side. So I'm going to shade below that line. Now I'm above the y equals 0 line. I'm below the one that I just graphed. And I'm to the right of the x equals 1. So this dark area that I've created, this triangle, that's my feasible region. So that's kind of the shape that we're looking at to do linear programming with. So we've taken care of the first part, we've graphed them. Now we have to name the coordinates of the vertices, which means where do these lines cross? Well, it looks like one's here at 1, 4. It looks like 1, 2, 3, 0 is another one. And 1, 0. So those are the coordinates of my three vertices. I have those listed. Now I have to find the maximum and the minimum value of this function that you see here. F of x and y equals 3x plus y. Well, what I'm going to do is I'm going to take my three ordered pairs and I'm going to plug them in for x and y. So if I plug x of a 1 in and I plug a y of a 4 in, I get 3 times 1 is 3, plus 4 is 7. So my value when I plug in 1 and 4 is a 7. Let's see what happens when I plug in my second vertice. 3 and 0, so I'm going to say 3 times x, which is 3, plus y, which is 0, and that gives me a 9. And then do the same thing with 1, 0. 3 times 1 plus 0 gives me a 3. So we have to find which one of those is the biggest number and which one of those is the smallest number. The maximum value is 9, and that's at point 3, 0. So I'm not only saying what the max, in fact I'll say this, the max is 9 at 3, 0, and the minimum value is 3, and that occurs at the ordered pair 1, 0. So taking each one of my ordered pairs and plugging it into my function, we find the maximum value happens at this point, and the minimum value happens at this point. Here's another example of linear programming. These inequalities are kind of difficult, so you might want to isolate the y in each case and see what the boundary line looks like. For the first one, I'm going to subtract 2x, so this is my first boundary line. Second one, I'm going to add x, and then I divide by 3. So it's going to be a 1/3 x plus 3. And for the last one, I'm going to subtract 2x, so negative 2x plus 10. So those are what my three new boundary lines are going to look like, and I'm going to graph them and then shade them and find the feasible region. So first one we'll do blue. 3 is my y-intercept. Slope is negative 2, so I'll go down 2 to the right 1, down 2 to the right 1. And because it is greater than or equal to, I'm going to use a solid line. If I plug 0, 0 into the original, I get 0 greater than 3. That's false. So 0 is on the bad side. So I'm going to shade to the right of this line. Second one I'll do in red. 0, 3 is also the y-intercept for that one. Slope is up 1 to the right 3. Up 1 to the right 3. Solid line because it's less than or equal to. Plug 0, 0 into the original. 0 minus 0 is 0. Is 0 less than 9? Yes. Since 0, 0 is here and it's true, I'm going to shade below this red line. Last one we'll do in green. The y-intercept is 0 at 10, which is here, and the slope is negative 2, so down 2 to the right 1, down 2 to the right 1. Again, it's a solid line because less than or equal to. Plug 0, 0 into the original. 0 plus 0 is 0. 0 is less than 10, so I'm going to shade on the 0, 0 side of the green line. And now we want to look and see where all three of them cross. And they all cross over in this region in here. Now this is an example of one of those unbounded regions because this goes on for infinity. There's no lower line on the bottom to keep this bounded. But we've now found our feasible region. We just have to find out what the vertices are. I see one here where they connect at 0, 3. And I see one up here where two of the lines cross, which is 1, 2, 3, 4. So the trick now is to find out which one of these two creates the maximum and the minimum for that function. So I'm going to take the x, y and plug them in. 0 for the x and 3 for the y. So that's a 0 plus 12. So 12 is one of my values, and then plug in 3 for x here and 4 for y here. So 15 and 16 is 31. So we'll say the maximum is 31, and that's at 0.34. Now what's interesting is we can say that the maximum is 31 because that's at near the top of the region, but the bottom part of the region is unbounded. So even though 12 is the smallest value that we're given, we don't know about a value that's smaller down here because there is no lower bound. So we would say that there is no minimum value, and that's because the region is unbound. So before we do another example, let's just do a review of what linear programming is. It's the process of finding a maximum or a minimum value of a region, and these are the steps that you take to do that. Here's an example of linear programming. I suggest that you pause the video, read through this problem, and then we're going to follow the 7 steps for linear programming. And the first step is define a variable. So after you read through it, try to find the two unknowns and assign them some variables. The problem asks us to find a combination of office visits and surgeries. Those look like the two variables that we should be looking for. So I'm going to say that V is the number of visits, and S will stand for the number of surgeries. Now that we know our two variables, we want to write all the inequalities that will constrain our region, that will create a shape that we'll call the feasible region. So let's go back and try to figure out what sort of lines we can graph. Since I know I can't have negative surgeries or negative office visits, I'm going to call this bottom axis the S-axis and this vertical one the V. And I know I can't be negative, so I know that my number of surgeries has to be bigger than 0. And I also know that my number of office visits has to be greater than 0. Those are just two constraints that fit this situation. I'm told in the problem that I can't have more than 6 surgeries per day, so I also know that my surgeries have to be under 6. Now they could equal 6, but they have to be smaller than that. And then my last inequality that I can build comes from this information. 20 minutes for an office visit, which means 20 times a visit, and 40 minutes for a surgery, so 40 times the number of surgeries. If I add that, I have to come under 7 hours because there's only 7 hours available. Now the trick is I'm not going to put this less than 7 because these numbers are in minutes and the 7 is in hours. So I'm going to multiply 7 times 60 and get 420 minutes. So these 4 inequalities represent the outside constraints for my feasible region. So now I'm going to graph. I'm going to graph these 4 inequalities and see what kind of shape I get. So this line here represents s equals 0. So this is the last s I can have, and since it's greater than, I'm going to shade everything above it. This line here is my v equals 0. It's the boundary v equals 0, a vertical line, and I have to have everything that's to the right of that. So far I'm going to be shaded into this region right over here. Now you see here that I've assigned some values to the s-axis and the v-axis, so I can begin to plot some more of my lines. S equals 6 is a vertical line right here. And because it's less than 6, I'm going to want the shaded area to the left of that. So far I've built what looks like a rectangular area, but it's not bounded on the top. And that's what this last line is going to do. It's going to bound it on the top. Now the last line that I've graphed is right here, and I found points. I found the y-intercept and the x-intercept by plugging in zeros for the other letter. And I found that 0.21 was a point and 10.5, 0 was a point, so I graphed that line. Because we're less than, we're going to shade underneath it. So here is my shaded region. This is my feasible region. This is the shape that I'm going to look at to do my linear programming. So now step 4 is find the coordinates of the vertices. So I have to find all 4 of these vertices that create my rectangular triangle type thing. Well, one of the points is up here at 0.21, so that's one of them I will choose. The other one's down here at the origin, 0, 0. There's a point that creates a boundary here at 6, 0. And the last one's right here. It's about 9. No, it's about 6 over and up 9, so 6, 9. So those 4 points form the vertices of my feasible region. Step number 5 is to write a function that I'm going to maximize or minimize. And that's where I'm going to use this information. Office visits cost $55. Surgeries cost $125. So I'm going to make a function using surgeries and office visits. And that's going to be $125 per surgery plus $55 per office visit. So this is the function that I want to maximize and minimize and find out what's the best way for me to maximize my profits. Step 6, substitute the coordinates. So I'm going to plug all 4 coordinates that I found that bound my region into this function. The last step, select the greatest or the least value depending on what the problem's asking for, and then answer the problem. Well, let's go back. We want to find out what will maximize my income. And that's what my function is. My function is a function of income. I'm looking at the number of surgeries and the number of office visits to make the biggest number, the biggest amount of dollars. And it looks right here like 1245 is the way to go. So that means if I have 6 surgeries and 9 office visits, that'll give me a max profit of $1,245.